Hi, in this presentation, we're going to discuss temperature and heat. So, as we learned last week, all matter is composed of atoms, and these atoms and molecules are always moving randomly, even in objects that appear to be solid and unmoving, like, say, your desk or your car or your wall. And these individual atoms and molecules have what we call kinetic energy, or energy due to their motion. And this kinetic energy can be detected as warmth. And if we measure this by a standard measure, we have a temperature. And temperature is basically just a number that we've assigned that corresponds to the relative coldness or warmth of an object. It's important to realize that when we talk about temperature, it's proportional to what we call the average translational kinetic energy per particle of a substance. Okay? And that's a ratio of energy per molecule. And translational motion means the particle has to be moving from place to place. Vibrating or rotating in place is also kinetic energy, but that's not affecting temperature. Only the translational, moving from place to place particles are affecting temperature. We can measure temperature by using a thermometer, which is just another word for thermometer. And thermometers work by having liquid in a sealed glass tube that's connected to a scale so that we can measure it. And this liquid expands or contracts when we expose it to environments or objects that have temperature. When the thermometer and the object we're measuring reach thermal equilibrium, the liquid stops expanding, and then we can take a reading. And if we look at our picture here, the thermometer on the left reads about 9 degrees Fahrenheit, which is pretty cold. And then on the right, our thermometer reads about 100 degrees Fahrenheit, which is fairly warm. On the previous slide, you heard me mention Fahrenheit, and Fahrenheit is one of the three common scales that we use to measure temperature. The most common scale and used in most of the world except for the United States is the Celsius scale. And Celsius is based on the freezing and boiling points of water. So 0 degrees Celsius is when water freezes and turns to ice, and 100 degrees Celsius is when water boils and turns to steam. Scientists took these 2 points of water and assigned 0 on one hand and 100 on the other, and then they divided the spaces in between into 100 equal pieces to give us the Celsius scale. And the Celsius scale is sometimes also called the centigrade scale. So Celsius and centigrade mean pretty much the same thing. The Fahrenheit scale that we use here in the US is a little different. And it was developed by a scientist in the early 1700s, and he was studying saline solutions. So he took the freezing point of his saline solution as 0 in his scale, and the temperature of what he thought was the temperature of the human body as 100. And of course, we know even on the Fahrenheit scale, it's not 100, but we'll let that go for now. So his scale went from 0, the freezing point of his saline solution, to 100, or what he thought was the temperature of the human body. And you'll note that in this scale, the freezing point of water is not 0, it's 32 degrees Fahrenheit, because of course saline solutions freeze at a lower temperature than water. And also the boiling point of water is 212 degrees Fahrenheit, so a little different from our Celsius scale. Also, when we compare these two scales, you might notice that between the freezing point and boiling point of water in Celsius, there's only 100 degrees. But between the freezing point and boiling points of water in Fahrenheit, there's 180 degrees. So we can see in Fahrenheit, each degree is only about 5/9 of a degree in Celsius. We also have a third measure for temperature, and that's the Kelvin scale. The Kelvin scale is often used in science, especially when we're talking about astronomy or other topics dealing with extreme temperatures. In the Kelvin scale, 0 is not related to water or solutions, but 0 in the Kelvin scale is absolute 0. And absolute 0 is when there's no translational kinetic energy left in a substance. Basically, the atoms of that substance are not moving at all. When Lord Kelvin developed this scale, he determined that each degree in his scale was going to be the same as a Celsius degree. So for each degree we go up in Kelvin, we're going up 1 degree Celsius. So when he measured from absolute zero to the point of water freezing, that would be 273 degrees Kelvin. And then to the boiling point of water would be 373 degrees Kelvin. And so if we want to convert between Kelvin and Celsius, it's pretty simple. If we have a Kelvin temperature and we want to find out what the Celsius temperature is, we just have to subtract 273 degrees. Or if we have a Celsius temperature and we want a Kelvin temperature, we just have to add 273. If we want to convert though between Celsius and Fahrenheit, it's a little bit more difficult because our degrees are not equal. Again, that Fahrenheit degree is only about 5/9 of a Celsius degree. So our calculations to get between Fahrenheit and Celsius are a little bit more complex. When we talk about heat, we're talking about an internal energy that's being transferred from one thing to another due to a temperature difference. One object is hotter than the other object. And it's important to realize that matter doesn't contain heat. Matter contains that molecular kinetic energy, translational, vibrational, etc. When we talk about heat, we're talking about that energy that's in transit or moving from one object to the other. Once that energy is transferred to the second object, then again, it's no longer heat, it's internal energy in the second object. So heat is only energy that's in transit. And when we talk about internal energy is a total of all energies that's stored inside a substance. And remember, when we talked about temperature, that's only the translational kinetic energy. But internal energy is all the energy, translational, kinetic, vibrational, rotational, etc. When a substance gives off or absorbs heat, its internal energy is either going to decrease if it's giving off heat or increase if it's absorbing heat. And heat always, always, always moves from a higher temperature object to a lower temperature object until thermal equilibrium is reached. Okay? Heat can never flow from a low temperature object to a high temperature object unless we add some type of resistance or energy. And this is true regardless of whichever object has more internal energy. So let's look at this picture to see this in action. So over here on the left, we have a backyard pool and it's filled with water and it has billions upon billions of atoms of water in the pool. And all these atoms of water have translational kinetic energy, they have vibrational energy, and they have rotational energy. So the internal energy of this pool of water is going to be very high just due to the amount of atoms that we see there. Over here on the right, we have a picture of an iron horseshoe, and that horseshoe's been heated up red hot. And again, just like the pool, it has translational energy, kinetic energy, vibrational energy, rotational energy. But because it's so much less massive than the pool, its internal energy, the sum of all those energies, is going to be much less than the pool. Even though the temperature that we can measure of the horseshoe is much higher. So the internal energy of the pool is always going to be greater than the internal energy of the horseshoe due to the difference in mass and the amount of atoms that comprise both of them and contribute to the total amount of internal energy. But now what happens if we take this hot horseshoe and dunk it in the pool? Which way is the heat going to flow? And of course the heat is going to flow from the hot iron horseshoe to the pool, even though the pool does have greater internal energy. But heat is always going to flow from a hotter object to a cooler object, no matter how much internal energy either one of them has. Okay? And the iron horseshoe is going to transfer that heat to the pool until both objects are in thermal equilibrium so that the temperature of the horseshoe is now the same as the temperature of the water in the pool. Heat is commonly measured in joules, which we saw joules back when we talked about energy and work. And heat can also be measured in calories. And a calorie is defined as the amount of heat that's needed to change the temperature of 1 gram of water 1 degree Celsius. And that amount of energy comes out to be about 4.19 joules. So you can hear people measure heat either in joules or in calories. Now, this calorie that we just described is sometimes called the small calorie. And as you can see, it's written with a small lowercase letter c. The calorie that we use to measure the energy of the food we eat is actually the kilocalorie, which is written with a big C. And of course, since it's a kilocalorie, it's 1,000 small calories. So if you have a cheeseburger that you eat that says it's 400 calories with a big C, it actually has 400,000 small calories. If we look at different substances, we notice that some substances or materials can store more internal energy or less internal energy than other substances. And some heat up faster, get hot faster, and some cool off faster. And we call this capacity of substances to store internal energy its specific heat capacity. And different substances have this different specific heat capacities due to the fact that they absorb or emit energy in different ways. So if we have two objects that are absorbing the same amount of energy, one object, say, might absorb that energy in the proportion of maybe 50% translational energy, 30% rotational, and 20% vibrational. But our second object might distribute that same amount of energy in a different proportion, like say maybe 45% translational and 25% rotational, and that leaves what, 30% vibrational. So they're absorbing the same amount of energy, but they're storing it in different proportions. So specific heat capacity can be defined as the quantity of heat needed to change the temperature of a unit of a substance, and usually we're talking about 1 gram of a substance, by 1 degree Celsius. And you might say, hey, wait a minute, this sounds an awful lot like the small calorie we just discussed a couple of minutes ago. But remember, in the small calorie, we're talking about the energy needed to change the temperature of a gram of water by 1 degree Celsius. Specific heat is going to be the amount of heat needed to change the temperature of any specific substance by 1 degree Celsius. Another useful way to think about specific heat capacity as the thermal inertia of an object. So it's a measure of an object's resistance to changing its temperature. And we can kind of do a little thought experiment to talk about specific heat capacity. Let's say you had a kilogram of water and you put it in your big spaghetti pot and you put it on the stove. And when you turn the burner on, it's going to take about 15 minutes for that water to absorb enough energy to reach its boiling point, 100 degrees Celsius. Now let's take a kilogram of iron, throw it in a pot, put it on the same stove. When we turn the burner on, it's only going to take about 2 minutes for the iron to reach 100 degrees Celsius. So much, much less time than the water. And this is because these equal masses of these two different substances need different quantities of heat to change their temperature by whatever number of degrees we've specified. The water, again, to raise 1 gram of water would require 1 calorie of energy to raise the temperature 1 degree Celsius. If we look at iron, to raise the temperature of 1 gram of iron 1 degree Celsius, it only takes an eighth of a calorie. So it takes much, much less energy to get the same temperature increase in a gram of iron as you would need for a gram of water. So we can say that water can absorb a lot more heat than iron for the same change in temperature. Our kilogram of water absorbed much, much more energy before it reached 100 degrees Celsius than our kilogram of iron did. So we say that water has a higher specific heat capacity, and we can also see by looking at this another way that a relatively small amount of water can absorb a lot of heat, a large amount of heat. And also, because water, it takes a long time for water to heat up because of its thermal inertia. Once water is hot, it takes a relatively long time for it to cool off. In fact, water has the highest specific heat capacity of all commonly known substances, and this makes water very useful to us to use in cooling systems where we need to remove heat from a system. For instance, let's look at the engine in your car. Most cars use internal combustion engines, so gasoline is burned, and the heat and from that reaction moves the pistons in the engine, which turn the camshaft. And of course, one of the byproducts of using that energy of gasoline to turn our pistons is it produces a great deal of heat. And if we didn't take that heat away from your engine somehow, the heat would actually cause some parts of your engine to get hot enough to melt and fuse together. And then your engine, of course, was not going to work anymore. So, water is commonly used in the cooling systems for these internal combustion engines because that water can absorb a lot of heat without raising its own temperature very much, take it away from the engine, and then disperse it into the environment, usually through a radiator. We can also use water to cool things like nuclear reactors. In the core of a nuclear reactor, as that nuclear reaction is ongoing, it creates a great deal of heat. And if we didn't take that heat away from our core, then the core could actually melt down and escape the reactor, which is generally seen to be a bad thing. So we can use water to pull heat away from the core, cool off the core, and then in most cases that heated water is used to drive turbines and create electricity. This high specific heat capacity of water also affects climate, as we look in this picture here of the ocean currents moving around the world. And take a closer look at the Gulf Stream. The Gulf Stream starts in the Gulf of Mexico, moves around the tip of Florida, and then goes up the coast of North America and over towards Europe. So the Gulf Stream is actually transporting heat from the Gulf of Mexico and the Caribbean, which are very warm oceans, all the way over to the coast of Northern Europe. And this is why cities in Northern Europe, even though they're on the same latitude as cities in the US and Canada, are much warmer in winter than those cities in North America. For instance, you can look at, say, a city like London in England, which is pretty much on the same latitude as Maine in the US, and winters in London are much milder than a winter in Maine. And this is basically just because of the heat that the Gulf Stream, that water, has transferred from the Gulf of Mexico and the Caribbean to Northern Europe. This also works in the continental United States as well. Um, in the western part of the United States, the west coast of the United States and Canada, the prevailing winds move air from over the Pacific Ocean over the land. And the Pacific Ocean, the water holds heat. So in the wintertime, it creates a warmer winter because this warm air is moving, that's relatively warmer than the land, is moving over the land. It also cools the air in the summer. So at this point, uh, the air moving from the water is cooler than the land, so it cools the air over the land. Okay? So we see that the Pacific coast has a relatively mild climate compared to areas on the East Coast in similar latitudes. Uh, on the Pacific coast, there's not a whole lot of difference there's not a big change between the winter and summer months. Okay? However, here on the East Coast of the US, air moves the other way from over the land over the to over the Atlantic. And so the land gets hotter much more quickly in the summer than the water does, but it also cools much more rapidly than the water does in the winter. So we have hotter summers because we don't get that cooling effect from the water, and we also have colder winters at, if you look at the same latitudes compared to the west coast. And we also have a greater difference in our seasons. Our summers are hotter and our winters are colder. As objects absorb more heat, the temperature of the object goes up. And if we looked at the molecules that comprise that object, as they absorb more energy, more heat, the molecules inside the object start to move faster and move farther apart. And so as things get hotter, they have a tendency to expand. And as things get cooler, those molecules are moving slower, moving closer together. And so most objects contract when they get cold. We call this thermal expansion. And we can see, like, say, if someone's laying some railroad tracks. If the team laid the railroad tracks on a winter's day and didn't take thermal expansion into consideration, on a hot summer's day, when the steel of the railroad tracks expanded, then the tracks could actually buckle and become unusable. And you can even use thermal expansion in your kitchen. Let's say you get a jar of pickles or something out of the fridge and the lid's on tight, you can't open the jar, you can't get the lid to budge. If you run the lid of the jar under hot water in your sink, the metal lid expands faster than the glass does, and now the lid is looser and you can probably open your jar. And again, the glass has a higher specific heat capacity, so it absorbs more heat before it expands than the lid does. We can also see construction devices and techniques that use thermal expansion. If you've driven over a bridge, you might have noticed something that looks something like the picture here. It looks like a big zipper laying in the road. And that's actually an expansion joint. So that as the bridge contracts or expands, either due to colder weather in the winter or heat in the summer, the expansion joint allows the bridge to stay structurally sound by taking up some of the movement of the bridge due to that thermal expansion or contraction. And if you're walking on a sidewalk or on a concrete roadway, you notice that they don't lay the sidewalk or the roadway in just one big ribbon. It's usually in sections. So it's, a little section, maybe a little gap, and then another section. Okay. And there's gaps in between these sections, and the roadways, they might be filled with tar or something like that. And again, this allows for expansion of the concrete slabs in the summertime and contraction in the winter, and it can prevent the concrete from cracking. And different substances, as they absorb heat or lose heat at different rates, can also expand or contract at different rates. And we can use this property to make devices like thermostats. And thermostats often work on what we call a bimetallic strip. And so these bimetallic strips might be made, say, of brass on one side and iron on the other, as in our picture here. And these are stuck together. And at room temperature, if you look at the middle of the picture, they're both perfectly straight. They are at the same length. But let's say we start cooling our strip. And as we cool our strip, the brass contracts faster than the iron. And now we see that the strip is curved. And the same thing happens if we heat the strip. The brass expands more than the iron, and now it curves the other way. And to see how this can work for us, let's look at the thermostat in our fridge, for example. So you set your refrigerator to a certain temperature, and the compressor kicks on and starts to cool the fridge, and our bimetallic strip starts to bend towards the brass side. And as the bimetallic strip bends and reaches a certain area on the thermostat, it, say, loses contact with the switch, and the compressor kicks off. And then as the refrigerator starts to heat up over time, the strip bends back the other way and makes contact with the switch. The compressor clicks back on and cools your fridge some more. And this is the same way that thermostats work, say, in your oven, your heater, your air conditioner, and even electric toasters. When we examine thermal expansion of objects, you might notice that a lot of time it's greater in liquids than it is in solids. And you can do an experiment with this if you, say, go camping. And let's say you brought a can of soup that you want to have for dinner, but you forgot a pan. So you can heat up your can of soup just by putting it in the fire. And you set the can in the campfire, it starts to heat up the soup. But you have to be careful here, because if you haven't made an opening in the can, the soup expands more than the can, and then when you open the can, the soup will expand very rapidly and can come out and burn you. So if you're going to do this, you might want to make a small hole so that some of the soup can escape the can as it heats. And water, like most substances, expands when we heat it. Okay, so if we take a pan of water and put it on the stove as it heats, the volume of that water actually increases. But water can be kind of weird um, in some ways because if you heat water from 0 Celsius, the freezing point of water, to about 4 degrees Celsius, the volume of the water actually decreases. So it contracts as we heat it. So, how can this be happening? How can water act so weird? And to explain this, let's first look at some frozen water, which of course is ice. When water freezes, when water becomes ice, it forms a crystalline structure. And if you look at the picture on the left, we can see here's our liquid water. The molecules are kind of moving around and they're pretty close together. This is a relatively dense liquid. And the molecules are close together, but they're not really attached to each other in any way. They're just kind of hanging around. As the water freezes, the molecules make these connections you can see with each other and on the right hand side of the picture, and they form crystals. And these crystals actually take up more room. You can see the molecules of water are actually further apart when the ice freezes than that they were when it was liquid. So the volume of the water is actually going to increase as it freezes. And because the volume is increased, we have fewer molecules in the same amount of space. So the ice is less dense than the water, and this is what makes ice float in the water. If we keep cooling our water below 0 degrees Celsius, our solid ice is going to contract further as we would expect it to. Things contract when they cool. But due to the crystalline structure of the ice, the density is always going to be less than water. You can't cool ice, water ice, cold enough to make it denser than water. So this is why I say if we go to the Arctic or the Antarctic, we see icebergs floating in the cold sea. The icebergs float and never sink to the bottom of the ocean. And they're going to float no matter how cold they get. They're still going to float because our ice can never be denser than the water. And you can see this when, say, lakes or rivers freeze. And when they freeze in the wintertime, the ice forms at the top. We don't see ice forming at the bottom of the lake or the river. It forms at the top so that we can go ice skating or ice fishing or whatever. But now let's start warming up our ice and see what happens. At 0 degrees Celsius, the water is ice, but as we slowly raise the temperature, some of that crystalline structure of the ice starts to break up and some of the crystals melt. Okay? Some of them are melted, but some still remain. So at a little over 0 degrees centigrade, this makes a slush that has a slightly larger volume than water. As we keep increasing the temperature of our water, the remaining crystals collapse. And so this makes the water contract. And now we have two forces acting against each other. With the collapse of the crystals, it makes the water contract. But now we also have that expansion due to the increased internal energy as we increase the temperature. So we have two forces working against each other, collapse of crystals and expansion due to internal energy. The molecules are moving faster and faster and moving apart, but we also have crystals collapsing inwards. So we have collapsing inwards, expanding outwards. Up until about 4 degrees Celsius, the collapsing effect dominates. So as those but as those crystals melt, the collapsing effect dominates. So we can see that the volume actually shrinks. Once we hit 4 degrees Celsius, all the crystals are gone. And now that expansion can take over and the volume increases just like we would expect it to as we increase the heat. And so you can see in this diagram over on the far left at 0 degrees, we have our frozen ice. As we heat up the ice, the crystals collapse and the volume of the water actually decreases. But then once we hit 4 degrees Celsius, all the crystals are gone. And now our water can freely expand, and it will expand like we would expect it to with increased heat. So we've talked about heating objects up and cooling them down, but now let's talk about heat transfer and how heat moves or energy moves from one object to another. If we have objects that are at different temperatures and they're in thermal contact, they're going to want to try to reach a common temperature. And they can transfer that heat in three different ways. They can transfer it by conduction, convection, or radiation. So let's look at conduction first. When we have a substance in which the free electrons can kind of move and collide with other free electrons, they can conduct heat and energy more readily than other materials. And these materials that conduct this energy more readily are called conductors. A good conductor conducts heat quickly, and these are usually substances with loosely held electrons, so that those electrons can transfer that energy quickly to other electrons throughout the solid. Most metals are good conductors of heat. The best conductor of heat is silver, followed by copper, and then the other solid metals. And most items that are good conductors of heat are also very good conductors of electricity, and we're going to talk about that in a couple of weeks. While some solids like metals are very good conductors, other solids, say, take for example wood, are not good conductors. And let's say you get out of a bathtub and you stand with one foot on a wooden floor and the other foot's on a tile floor. Which one do you think is going to feel colder? And you probably will say the foot that's standing on the tile floor will feel colder. And that's because the tile is a better conductor. It's better at conducting the heat away from your body. If we have a substance that's a poor conductor, we call that an insulator. And this is usually substances where the electrons are more tightly held than they are in a conductor, so the electrons tend to vibrate in place, and they transfer energy from one molecule or atom to another very slowly. So things that are good insulators are going to be poor conductors, and vice versa. Things like glass, wool, wood, paper, cork, styrofoam, all are very poor conductors, but are very good insulators. Air, like most gases, is a very poor conductor, but it's a good insulator. And you can see this in everyday life. Let's say you're cooking a pizza in your oven and you want to reach in and maybe want to rotate that pizza so all edges of it get done at the same time. You can reach into the oven and put your hand in this hot oven without getting burned, even though the oven is like at 450 degrees, because the air is a poor conductor of heat. So it's not conducting the heat of the oven to your hand. But now what happens if, say, you accidentally let your bare hand touch the rack in the oven? Well, ouch, you're going to get burned, right? Because metal is a good conductor and it's going to conduct that heat to your hand. Since air is a poor conductor, any substance that traps air is going to be a good insulator. So the wool on sheep that we make sweaters out of traps air and is a very good insulator. An animal's fur is a good insulator, and it's not the fur itself that keeps the animal warm, it's the fact that the individual hairs of the fur trap air, and that air is the good insulator. Same thing with the feathers on a bird. And even snow itself is a good insulator. The air pockets between individual snowflakes make snow a great insulator. And you can see this with Arctic animals will sometimes burrow in the snow, and between their fur and the insulation by the air pockets in the snow, they stay pretty warm. Wood is a good insulator even when it's red hot. And that's one reason you can see these videos of people fire walking. They're walking on the red hot coals barefoot. And the reason the man, for instance, in this picture here is not getting burned is because wood is a poor conductor and it's not transferring that heat to his feet. Okay. I would not recommend trying this at home, for instance. A lot can go wrong if the fire pit is too deep and your feet sink into the fire, or some other things can go wrong. So don't try that at home. But it's not some type of magic or anything like that. It's just based on the wood being a poor conductor and a very good insulator. It's important to remember that insulation doesn't prevent the flow of internal energy, it just slows the rate at which this internal energy flows. As far as we know, there's no 100% effective insulator. So the insulation in your house doesn't prevent the heat from your house from going outside, it just slows the transfer. The second way that heat can be transferred from one object to the other is convection. And before, when we just were talking about conduction, the objects have to be in contact with each other for the heat to go from one to the other. But with convection, we're talking about the transfer of heat with the motion of fluids. And convection can occur in all fluids, whether they're liquids like water or gases like air in our room. Let's look at the convection of air. In the top of this picture, the radiator is heating the air in the room. As the molecules are close to the radiator get heated up, they expand, and this air becomes less dense, and so it goes upwards towards the ceiling and keeps rising until its density equals that of the surrounding air, and then it cools and falls down and moves to the bottom until it comes close to the radiator to get heated again, and that cycle repeats. So as the radiator heats the air, it creates this kind of circular motion of hot air rising and cooling and falling and becoming hot again and rising. And the same thing happens to the water in the pan. As the water closest to the bottom of the pan gets warm, it moves up, transferring that heat throughout the fluid, and then cools and falls down to be reheated. We can see this convection in the creation of winds on planet Earth as well. Wind is a result of the uneven heating of the air near the ground or the water. As the Earth absorbs energy from the sun, certain parts of the Earth absorb it more readily. So, for instance, the ground absorbs the energy from the sun more readily than the water does. We just said in the previous slide that the surface of the Earth is warmed by energy from the sun. But how does that energy get from the sun to us? Is it by conduction? Well, no, because the sun isn't touching the Earth. Is it by convection? Well, no, again, because there's a vacuum of space between the Earth and the sun, so there's no fluid to be set in motion. The energy from the sun gets to the Earth by radiation. Radiant energy is an electromagnetic wave, and the electromagnetic spectrum comprises a lot of different energy, all the way from radio waves up to light waves and beyond. Electromagnetic waves can transfer energy, and they can either have long wavelengths, such as radio waves and microwaves, to very short X-ray wavelengths, such as X-rays. And in the visible spectrum, we can see red, which is the longest wavelength we can perceive with our eyes, all the way to violet, which is a much shorter wavelength, which is the shortest wavelength that we can perceive. The wavelength of radiation that an object emits is related to the vibrational frequency of that wave source. So if we have a low frequency vibration, it's going to produce a long wavelength. And then a high frequency vibration will produce a short wavelength. And we can see this in the picture of our little girl. She has a jump rope attached to a wall. If she jiggles the rope fairly slowly, we'll see these very long wavelengths, as we see in the picture on the left. If she starts jiggling the rope much faster, we'll start to see a higher frequency vibration and waves with a much shorter wavelength, as in the picture on the right. Every object that has a temperature above absolute zero radiates energy. So from the sun, we get electromagnetic radiation, or sometimes called solar radiation. And from the Earth's surface, we also get terrestrial radiation, which is usually in the form of infrared waves that we can't see because they're below the visible spectrum. Our eyes can't actually perceive infrared waves. Objects at room temperature also emit radiation. So objects like the chair, the walls of the room you're in, emit radiation in the infrared. And again, we can't see those waves. They're too long for us to perceive. Once we heat an object up to about 500 degrees centigrade, then we start to see it emitting a red light. And this is the longest wavelength that we can perceive with our eyes. About 1800 degrees centigrade, a yellow light is emitted. And then at 5000 degrees, objects emit white light, which contains the entire range of visible light that we can see. And you might think, wow, 5,000 degrees, that's really, really hot. But the light bulbs in my lamp aren't that hot. They'd be burning the lampshade or whatever. But actually, inside the light bulb is a little filament that's usually made out of tungsten or titanium. And inside that light bulb, that little filament actually does get to about 4,900 degrees. So it's a very hot little filament, and that does, in most cases, emit almost the entire spectrum of visible light. So if everything is emitting energy, where is it all going? Where's all this energy going? Well, in addition to everything emitting energy, such as your chair and the walls and light bulbs, everything also absorbs energy. Okay? And any material that absorbs more than it emits is called a net absorber. And any material that emits more than it absorbs is a net emitter. So think about if you go to the beach and you lay down a dark, maybe a black beach towel on the sand. That dark towel is going to absorb more energy from the sun than it emits back. So it's a net absorber. And the sun itself is emitting much, much more energy than it absorbs. So the sun is a net emitter. When we talk about the visible spectrum items, items that we perceive as dark absorb energy better than lighter ones. Okay? And actually, that sentence is written kind of backwards because the reason we actually perceive objects as dark is because they've absorbed that energy in the visible spectrum. So in the visible spectrum, the darker something is, we can say the more energy it's absorbing. And in the infrared spectrum, absorption is more affected by the texture of a surface. So outside the wavelengths of visible light, texture is more important than, say, the color of the object in visible light. A duller, rough surface in infrared is going to absorb that energy better than a polished surface like a piece of metal or a mirror. The net absorption or emission of an object is going to be relative to the temperature of that object's surroundings. So if the surface of the object is hotter than its surroundings, it's going to be a net emitter, and it will gradually go cooler as that heat is transferred from the object to the environment. If the surface is cooler than its surroundings, then it's going to be a net absorber, and it's going to gradually grow warmer as energy is transferred from the environment to that object. And we can kind of understand this by thinking about maybe I decide to have a cup of hot coffee and I bring it to my desk and I sit down and I start doing some work and I forget about my coffee and don't drink it right away. The coffee, of course, is hotter than the air in the room. So the coffee is going to be a net emitter. The surface of the coffee is hotter than its surroundings. Okay? And it's going to transfer its heat to the air of the room and gradually grow cooler until, and it will continue to transfer its heat to the environment around it until they reach thermal equilibrium and the temperatures are the same. But now, let's say later on in the day I get thirsty again, but this time I get a glass of iced tea, bring it to my room, and the iced tea is cooler than the air in my room. So the iced tea is going to absorb energy from the air in my room. It's going to be a net absorber and will gradually grow warmer. Okay, until, again, thermal equilibrium is reached. So the coffee is a net emitter and will grow cooler. The tea is a net absorber and will grow warmer. And again, this is going to be relative to the temperature of the surroundings of my cup of coffee and my iced tea. The opposite of absorption is reflection, and objects that are good reflectors are usually very poor absorbers. If an object is a good absorber, it will reflect very little radiant energy, including light, back, which is why I said before that objects we perceive are dark are good absorbers because they absorb so much light that very little is reflected back to our eyes. Objects that are poor absorbers reflect a lot of energy, including light, and we perceive those as lighter colors. So an object that reflects little or no radiant energy will look pretty dark. So think about the pupil of your eye as the eye enters your uh, as light enters your eye, it's absorbed by the inside of your eye. So very little light is reflected back out of your eye. So the pupil, being that hole into your eye, looks very dark. It's not reflecting any energy back to us. Bodies that radiate more energy than they receive are going to become cooler. So remember my cup of coffee that I left sitting in my room. It um, transferred its energy to the environment of the room and it became cooler. So if you leave an object outside, like on your lawn on a cool night, it's going to radiate energy out into the cool air. But the cool air doesn't radiate very much energy back to that object in return because of the difference in temperature. If the item is a good conductor, it will that you left outside, it will conduct heat from the ground and then not become much cooler than the air. Okay, because it can conduct some of that heat that's being held by the ground. But what happens if the item that we left outside is a bad conductor? Then, as it radiates energy into the air, it's not going to be able to conduct much from the ground, and it can actually become cooler than the air surrounding it. And this is why sometimes you can get up on a cold morning and you can see frost on the grass even though it never got below freezing that night. Or sometimes you can come out and there's frost on your windshield of your car even though it never got below freezing the night before. And that's because the glass is a poor conductor and it actually gave off more energy than it received and became cooler than the air around it. When we talked about Newton's laws back when we were talking about the laws of motion, we talked about his first, second, and third laws, which have to do with mechanical objects. But Newton also formulated a law of cooling. And he said that the rate of an object's cooling is approximately proportional to the temperature difference between the object and its surroundings. So the greater the difference between the temperature of an object and its surroundings, the faster it's going to cool. And here you can see our little um, formula is just the tilde sign, which means proportional to, which is right there, the change in, or the difference in temperature. Okay. So let's say I have two apple pies that I just taken out of the oven. I've just baked them. So they're both equally hot and they have the same temperature. But let's say now I put one pie in the freezer and the other I just leave out on the kitchen table. So which one do you think is going to cool faster? Well, the temperature difference is greater between the pie in the freezer than the pie in the kitchen table. So the pie in the freezer is actually going to cool faster. Okay? And if we have two houses in the wintertime, the one that's warmer is going to give up more internal energy to the outside air than the cooler house. And Newton's law of cooling can also apply to warming as well. An object that's cooler than its surroundings is going to warm up at a rate that's proportional to the difference between the temperature between the objects and its surrounding. So if I have two frozen lasagnas and I want to defrost them for a big dinner, if I put one in the fridge and one on the kitchen table, well, of course, the one on the kitchen table is going to warm up faster than the one I put in the fridge. The difference between absorption and radiation can also account for something called the greenhouse effect. And the greenhouse effect got its name from when gardeners would build greenhouses and build those greenhouses in such a way that they could be warmer than the outside environment. And the way this happens is the short length radiation from the sun can get through the glass walls and ceiling of the greenhouse, and then the radiation is absorbed by the plants and the soil and tables and things inside the greenhouse. But remember, the objects inside the greenhouse also radiate energy, but they're going to radiate it at a much longer wavelength. And this long wavelength, as we can see in the picture, is unable to get back through the glass. So it's reflected back into the greenhouse. So as the sun heats up objects inside the greenhouse, those green objects in the greenhouse also radiate energy, but it can't get out through the glass, so the energy doesn't leave the greenhouse. And the temperature of the greenhouse then starts to rise compared to the outside environment. And with a greenhouse, you can actually raise tropical plants like, say, orchids or something like that in the wintertime in a northern latitude because the greenhouse is going to be so much warmer than the outside air. And sometimes people use greenhouses to, say, start plants uh, in the late winter, early spring so that they can have them ready to go outside when it gets warm enough. To understand how the greenhouse effect works, we have to realize that all things radiate at a frequency that depends on the temperature of that emitting object. And things are transparent, such as the glass of the greenhouse, depending on the wavelength of the radiation that hits them. In our picture before, the sun's light has a very short wavelength, so it can get through the molecules of glass, but the radiated energy from the objects inside the greenhouse has a much longer wavelength, and so it can't get through the glass. So we could say the glass is transparent to the sun's light, the sun's radiation, but not the radiation from the objects inside the greenhouse. The sun, being very hot, is vibrating at an extremely high frequency, so it emits very short rays of a very short wavelength. And again, just like penetrating the greenhouse, these rays can easily penetrate the gases of Earth's atmosphere, or they can go through, say, the glass of your car windows. And the car's interior is going to absorb that energy. And of course, as we've talked about, the interior surfaces of the car are also going to emit energy back. But do you think these interior surfaces of your car are emitting energy at a wavelength that can go back out through the car window? No, the car's interior is not near as hot or vibrating as at a high frequency like the sun, so the wavelengths are much longer, and these wavelengths can't pass through the glass of the car windows. So they're reflected back into the car and make that interior even warmer. So if it's 80 degrees outside the interior of a car with closed up window, I'm sorry, if it's 80 degrees outside, the interior of a car with closed up windows can get past 100 degrees in a very short period of time. And again, this is why you should never leave your cat or dog or your babies or chocolate in the car, because when you come back, your pet or baby could be in distress or your chocolate could be all melted. And this happens on a large scale in the Earth's atmosphere as well. So those short wavelengths from the sun can pass through our Earth's atmosphere. The Earth absorbs that energy, and then the Earth also emits radiation, but is at a much longer wavelength. And again, this longer wavelength can't go through our atmosphere's gases, just like the long wavelengths couldn't get back through the car window. And they're radiated back to Earth, and this contributes to the warming of the Earth.